Welcome to this NXP training session here at EE Live this week. My name is Andy Beeson and I am one of the LPCXpresso development team within NXP. And this afternoon I'm going to be talking about rapid embedded development using LPCXpresso. So just to get us going, we've got a few slides which are just going to give you a bit of background about LPCXpresso, and then we'll be spending the majority of the presentation actually running through a demonstration of using LPCXpresso in anger. But first of all, what actually is LPCXpresso? Well, it's basically an ecosystem, the primary parts of which are a variety of LPCXpresso boards and probes. So basically the LPCXpresso hardware, which we produce in collaboration with Embedded Artists, a company based out of Sweden. We have our LPCOpen MCU software. So this is basically our peripheral drivers and middleware support. And then we have the thing that I actually work on myself, which is the LPCXpresso IDE. So this is a software development tool chain, which is available for free of cost use by you, and we'll look at that in more detail in a few minutes. Now, one of the key things about LPCXpresso is that it is aimed at being suitable for use in evaluation. So basically, you get a development board, like the ones you'll get at the end of the session, which you can basically plug in and go with. You can also use it for prototyping, so you can take that evaluation board, change a couple of links on it, and use it to debug your own prototype hardware. And you can carry on using that probe on that board and the same software development tools for doing that. And then you can use it in your final development cycle as well. So you can plug it into your real development board, all of your engineering team carry on using that same debug probe and same software tools. Now, another key fact about LPCXpresso is that it is not a closed system. So we work very closely with a wide range of third parties. So in particular, I'm mentioning the ARM Mbed ecosystem, which some of you may be aware of. And that's something that our latest LPCXpresso version 2 boards support. And there's been a press announcement about that support made this morning. We also work with a wide variety of other third-party tool chains. So people like Kyle and IIR to make sure that they are playing nicely with NXP's MCUs. We've got board vendors, so people like Hightex, NGX, and a wide number of other ones. And also probes and middleware vendors, so people like FreeRTOS, Sega for MWin's, the MWin graphics library, and so on. And what we're trying to do is provide a solution for you that makes it as simple as possible for you to develop your own solutions around LPC MCUs. So in other words, we're trying to get you up and started as quickly as possible in your evaluation and then your development cycle. So what I'm going to do now is just look at these three items, the hardware, LPCOpen, and then LPCXpresso IDE in a little bit more detail. So LPCXpresso boards were first produced about 4 years ago now, and at the end of last year we started shipping a new generation of our boards, ones such as the ones I'll be demoing a little bit later on, and also you'll get at the end. So this is a development board that has a built-in debug probe in it, and we'll look at that debug probe in a bit more detail in a second. It's also got various peripherals, so we've got an onboard tricolor LED, we've got some user switches, and it also provides multiple expansion capabilities. So we've got LPCXpresso or Mbed connectors. So these are the traditional connectors that have been used in the LPCXpresso world, and they're the connectors that you can actually see in the middle of the board here. We've then also got support for Arduino Shield connectors. So those are the connectors running along the top of the bottom. So you could theoretically go off and get yourself an Arduino Shield, plug it in, write the software to drive that. Or you can use those connectors in the way that I've actually done on the setup we've got at the front here, which is basically just use them to plug a few jump leads in so I can quickly and simply connect a breadboard up. In this case, just to a few LEDs off the GPIO signals. We've also got the PMOD connector, which is the one there, which again is another industry standard connector. I mentioned Mbed a few minutes ago. We've now got Mbed support being rolled out for all of our LPCXpresso version 2 boards. So for the LPC 1549 board, that support is already there and out in the wild. For the LPCXpresso 11U68 boards that you'll get, that will be hitting the wild very shortly now. We also provide full LPCOpen drivers and examples for these boards, and we'll look at LPCOpen in a few minutes. And you can actually get a lot more information about these boards at the web link we've got down here. So I mentioned the debug probe built into these boards. So we've actually got 2 MCUs on board. We've got the target MCU, which is actually the MCU that you want to debug. So in the case of this board, the 11U68. And we also have a second MCU, which is an LPC 4300 family part, so our Cortex M4 part, which is being used as the debug probe. So we basically have 2 USB connectors in this example. One is connected to the target MCU, the other one is the debug link. So the debug link can be used in a number of different ways. First of all, during your evaluation cycle, you plug in your connector and you debug the target MCU. We can then also use it to debug an external MCU. So there's a couple of jumpers up here. We just change the links on those jumpers and the probe will then debug our own board for us. And we'll show an example of how easy that is to do later on in the presentation. With regards to what tools can actually talk to the debug probe that's built into these boards, the LPCXpresso IDE provides firmware that gets auto-loaded as soon as you plug USB in. So the first time we do a debug connection, firmware is downloaded onto the board, and that means we're always running the latest version of the firmware at any time. But we also offer broad tools compatibility with other toolchain vendors such as Kyle and AIR by having a number of other firmware versions available. So we've got SeamSys DAP, and also Sega J-Link compatible software. So this means if you don't want to use the LPCXpresso IDE with these boards, you can use your other favourite toolchain if that's what you want to do. The other thing that is sometimes useful is we can also debug the target MCU via the debug connector using another probe. So we've got our own favourite probe that we want to use rather than the built-in one. We can do that. And that, again, is what I'm effectively going to demonstrate later on when I'm going to debug one Xpresso board using the debug probe on another Xpresso board. Okay, so this is our new generation of board. It's slightly simpler, it's slightly different in format to the original LPCXpresso boards, which look like this one we've got here. So you can see it's actually a much thinner and longer form factor if you compare the two. We've still got that same debug connector, the LPCXpresso style connector in the middle there. And we've got multiple variants of these available, covering the full range of NXP's part family. So LPC 800s, 1100s, 1200s, 13 and 1700 families. So this is effectively our legacy parts. New generations of parts will be coming out on the version 2 board. We've again got a built-in link on here. It's slightly different in implementation, but the same basic principles. We can debug the onboard MCU, or in this case, we actually need to cut the tracks between the two halves of the board, and then we can use the debug connector there to actually debug, again, an off-board MCU. So you can do that very simply with just getting a Stanley knife and cutting the tracks there. Or in some cases, people go to more extremes and actually physically chop the board in two. Okay. The one difference between these two boards is that the debug probe on the old style LPCXpresso boards will only work with the LPCXpresso IDE. It's not compatible with any third-party tool chains. I just want to mention a couple of other boards that you may come across. I mentioned that the LPCXpresso version 2 board has this LPC Link 2 implemented in it. We actually have a standalone version of that debug probe as well. Same basic functionality, works the same way, downloads firmware exactly the same, but it's a little standalone board. And this can also act as a simple evaluation platform for NXP's LPC 4370 family, which are a triple core design. So they've got a Cortex M4 and 2 Cortex M0s in them as well. And again, more information on those on that link there. And then finally, we've got the LPC 800 Max board, which is a slightly simpler version of the LPCXpresso version 2 board. This is an evaluation platform for our low-end Cortex M0 Plus parts, the LPC 800 family. It's again got a built-in debug probe, but this time it's a CMSys DAP probe, so it works with a wide range of IDEs. And it also provides full embed support, so if you want to use the embed compiler from ARM, you can do that on that board in exactly the same way as you could use LPCXpresso with it. Again, more information on the web link that we've got there. So that's hardware. I mentioned we also provide MCU software. So LPCOpen is our solution for software drivers and libraries. One of the key points about it is we're trying to provide examples and drivers for all of the peripherals on each of our part families. So you get a driver for the peripheral, you get at least one meaningful example that shows how that peripheral and that driver can actually be used for each of the peripherals on the part. We've got common APIs across device families to ease porting from a low-end part to a higher-end part, for example. And the code base is all thoroughly tested and maintained. The other aspect of LPCOpen is the support that it provides for those commonly needed third-party pieces of IP. So this is things like graphics libraries. So we provide a version of Sega's MWin as part of LPCOpen. So you've actually got a version of MWin suitable for use on NXP's parts that have got LCD drivers, for example. And we've also got ports of open source software, so things like the FreeRTOS, the open source operating system used by many people, fat filing systems, and so on. So basically you've got this huge bundle of software that should hopefully provide you with most of the things that you need to get going with using your new MCU from NXP. So we provide LPCOpen in file format suitable for use for Kyle, IAR, and obviously LPCXpresso as well. And you can get lots more information and download the LPCOpen packages for the various MCU families from our LPCware site at that address down there. So what I'm going to do now then is move on to the main body of our presentation, where we're going to be looking in particular at the LPCXpresso IDE. So the IDE is basically an enhanced version of Eclipse, so the open source IDE platform, along with the GCC compilation tools. And one of the things that we're trying to do is provide something that is very easy to use and is very focused on ease of use explicitly with NXP's MCUs. So we put a lot of work trying to make this a much better working experience for you than going off and downloading the various components of Eclipse and GCC, trying to plug it all together. It gives you a single installer, which you download, install, and you've got everything ready to go. It's also cross-platform, so it runs on Windows, Mac, which is what I'm going to be demonstrating it on today, and on Linux. And we've got two editions of the product. We've got a free version, which has a code size limit of 256 kilobytes. And basically you go to LPCware, you download it, you register your installation, and you're away and going. And you can use that for evaluation, you can use it for full product development, so you can ship the code that you generate with this tool chain. We also have a professional edition which removes the 256K limit, and also gives you customer support via email instead of just forum-based support. And that's $495 US per seat. And there's lots more information and the downloads for LPCXpresso at that link there. So when you leave the presentation and you've got your board, this board here, if you open it up so that the stickers are removed, all of the links to go and download the software are on the back of the board. So Just out of interest, are there any people in here who have used LPCXpresso in the past? So we've got a few hands going up. The latest version of LPCXpresso is version 7, which has been released in the last month or so. It's based on the latest version of Eclipse, so the Kepler release of Eclipse comes with the latest version of GCC, which is version 4.83. And this is particularly interesting because it provides quite a lot of new optimization functionality, including one in particular, which is a new optimization level called -OG. And this is aimed at customers who want to develop, debug, and release exactly the same build of their code. So traditionally, many IDEs offer this debug and release build, which is exactly what Eclipse does as well. So you debug your code, you then rebuild it with optimization turn on, and hope that it then works. The aim of -OG is basically to remove that 2 steps to your development, so you just debug and release all of the same code at the same optimization level. It's also got support for various other things, so ARM, as part of their GCC development, have produced something called newlib nano, and we use that for C and C++ libraries, library support. And for C++ in particular, this provides quite a major code size saving over using the traditional version of newlib. So LPCXpresso version 7 supports all of the recently announced NXP parts, so LPC 1500, the 11U6X family, and also the 11E6X family, which was actually announced yesterday. Another piece of functionality that is interesting for some people is that we've now enabled GDB server debug connections within the IDE, and this in particular enables the use of the LPCXpresso IDE with Sega's J-Link probes. So if you've got a lot of J-Links sat around in your office and you want to carry on using them, you can now use those with LPCXpresso if you wish to. And version 7 is a free update for all users of LPCXpresso version 6. Okay, so what I'm going to do now is move on to the next part of my presentation. So I shall sit down and actually start using the tools. So to start off with then, I need to actually start up the IDE. And what you will normally see when you actually start the IDE is a workspace launcher pop up like the one we've got on the screen now. So a workspace is basically just a directory that contains the projects that you're currently working on. So each workspace can have multiple projects in it, and you can actually have as many workspaces in your system as you want to. It's just that a particular point in time, an instance of LPCXpresso will only be talking to one particular workspace. So if you want to move from one set of projects to another, you can just restart LPCXpresso and connect to that other workspace instead. The other thing that we've got here is that I always use this so that you can select the workspace at startup. If you're working on one set of projects, you're never going to change or not regularly going to change. There's a little tick box here so you can actually say, this is the workspace I'm always going to use, don't show me this dialog anymore. And that's something that quite a few people miss. So don't be afraid to tick it. It's very easy to change workspace when you're actually running the tools. So I'm going to select one of the workspaces I've got set up already, which is populated in the recently used list here, and click on OK. So LPCXpresso starts up, and we've got a default layout of the tools displayed here. So as you can see, we've basically got a layout that consists of a number of sub-windows. And the way that these sub-windows, or views in Eclipse terminology, are laid out is a thing in Eclipse terminology called a perspective. And in LPCXpresso, by default, we have a bespoke perspective we call the developer perspective. And the aim of the developer perspective is that you actually use the same perspective for both developing your code in your projects and for debugging them. So quite often in IDEs, you will actually have a separate C, C++, environment and a debugging environment. You can still do that if you want to in LPCXpresso, but the develop perspective is meant to combine those things into one instance, which for many users is much easier to get used to using. So the default perspective, so the develop perspective, has basically got 4 subsections that we've got displayed here. We've first of all got over here on the left-hand side the Project Explorer view. And you'll notice that we also have a number of other views tabbed in line with that. So we're not interested in these at the moment, but we can very easily flick to them when we're debugging, for example. We can look at the peripheral registers. And one of the powerful features of LPCXpresso and Eclipse generally is that we can relay out these views to match our exact requirements. So let's say I want to have the peripheral view always accessible. I can just drag it, and it becomes accessible in another location on the screen. Similarly, I can drag my register view across, and it again becomes laid out in a different fashion. So it's very easy to make the environment look like you want it to work. But if you get yourself in a mess, it's again very easy to actually fix that. We can just right-click on the develop button on the right-hand side, select reset, and it will put things back to how they were originally, so we don't get into our mess. On the right-hand side here, we have the editor view. And by default, when we start up LPCXpresso, we get a window displayed in the editor view called the welcome screen. And this is basically useful information about using LPCXpresso. So for example, we can click on the link to open the user guide, which actually explains how to get started with actually using the IDE. So once you don't want to see the welcome screen anymore, you can basically disable it in a preference so it won't appear anymore. But what you were normally doing inside the editor view is displaying source code and editing it. So I'll just open a couple of source files there. You can see that again, by default, these get tabbed, but if we want to separate them, we can again drag the windows around and relay out the screen. So I'll just close that one. The editor itself is a powerful editor, contains functionality that you would expect in an IDE. So you can see straight away that we've got syntax coloring provided. We can open and close comments up. Scroll down a bit, we can open and close functions. So basically we can collapse things and expand things to make what we see on the screen at any one time match the task that we're actually carrying out. Quite often you might actually want to modify code. So one of the things you might want to do, for example, is put a for loop in. We can actually automatically insert a number of code templates. So for example, if I want to put a for loop around that call to the board init function, I just select to surround it and it's automatically populated, and I can go in and edit that to match the variables I'm going to use and so on. So I'll just cancel that. Down in the bottom right-hand side of the screen, we've got a number of views tabbed, most of which we're actually going to use when we get to this point of debugging, but 2 which are very important when editing our code are the standard console and the problems view. So the console is where we're going to see our log when we carry out a build, so we can see the compiler invocations and any messages that they generate. And the problems view contains a summary of any errors and warnings that were generated as part of the compile. And we'll see how those work in a second. But then on the left-hand side at the bottom, we have potentially the most important view inside LPCXpresso, which is the quick start panel. So one of the things that people often find with vanilla Eclipse is it's quite difficult to actually work out how to get going, how to carry out simple tasks, and how to configure the system. So what we've done is we've tried to put some of that commonly used functionality onto the quick start panel, so that rather than having to faff around through levels of menus, we can basically just click on a single button and we're away. So we've got options to do things like import projects, create new projects, then build and debug. So what I will do first of all is we'll just select one of our projects and use the build option. So we can see down here on the right hand side the console view has now updated, and we've got a list of the compiler commands that have actually been executed. The link command down here at the end, and then finally we have what's called a post-build step, which just contains information regarding the size of the application that's been generated. So this gives us a quick idea of how much ROM, or rather flash, and how much RAM we've actually used for this application. So if I actually just go in and edit one of the sources in that file and add a problem to it. So if I just remove a semicolon, because that's a nice easy way of getting an error generated, and we build again. This time you'll see that we've got an error message generated. So if I actually just click on the error message, it takes us back to the right line in our source code so we can fix the cause of that problem. Now if you imagine you've got a code base where you had lots of errors and warnings, scrolling through the build log is not necessarily the easiest way of spotting them all, and that's where the problems view comes in. So again, we can use the problems view to quickly jump to the line where we need to actually fix our code. So just to prove I've fixed that, we'll build it one last time, and there we have it. So that's building an existing example. One of the things we're obviously going to want to do is create new projects though. And there are a couple of ways of doing that. First of all, when we're using LPCOpen, I mentioned the fact that we have each of these examples for each of the peripherals on the system. So sometimes you might want to just copy one of the existing examples and create a new project from that. And we can basically do that by using the copy and paste function. That's not always a sensible place to start though. And so what we also offer is a range of new project wizards, which allow you to generate new projects tailored exactly to the part that you're generating code for and using the options that you actually want. So I've started off by just clicking on the new project wizard, and we've basically here just got a selection of different part families which we may be wanting to generate our project for. So in the case of the board we've got here, it's an LPC11U68. So I'll open up the LPC11s, and we can see here in the middle we've got the 11U6X parts. So I'll again open that up. And we then end up with a list of available project wizards that we can run for this particular part. And these are broken up into a number of different groups. So if I just move that. So we've got a number of C projects, so both application and library projects. Similarly, we have C++ application and library projects. But we then also have a bigger grouping, so we have projects suitable for use with LPCOpen. And then because we know we have customers who don't want to use our example code, they're going to be using their own code all the way through. We've also got some simpler C projects that you can make use of as well. But the recommended direction these days is to use LPCOpen. So I'm going to select an LPCOpen project, and we'll just give it a name. So test 1. Click on next. We now get the option to actually select the exact part that we're going to be using. And this is quite important because in particular, it means that the tools know the exact details of the memory available on that part. So we know how much flash we've got, we know how much RAM we've got, and that controls things like the automatic generation of linker scripts. So by selecting the right part, you make sure your code is appropriate for the part you're running your code on. The next page of the wizards offers us the ability to select some library projects. So I mentioned that in LPCOpen, we've got these peripheral drivers for each of the peripherals on each of the chips. What we also provide as part of LPCOpen is a board support layer, which basically wraps those peripheral drivers with things like pin muxing information, functions to do things like turning LEDs on your board on and off, and so on. And that code is broken down inside LPCXpresso as a chip library and a board library. So these are library projects that build into archives, not into actual projects. So when we create our own project, what we need to do is select the chip library and the board library that are appropriate for the project's chip and boards that we're going to be targeting. Now, in most cases, those will be called LPC chip for the actual drivers and LPC board for the board support package. So I can select those from within the workspace using a workspace browser. Or also, for the commonly used ones, I also provide those inside a drop-down. So we can just quickly and simply select the right chip library and the board library for the LPCXpresso board here. And that means that basically once we've generated our code, all of the appropriate links into those library projects, header files that they provide, link into those archives will all be automatically set up for you. We then have a number of different option pages as we run through the rest of the wizard. There are full details of all of these in the user guide, but typically for most of them you can just accept the default options. They're really just there for when you get to a more advanced level. So for now, I'm just going to click them all as next. And then I get to the final page and I can click on the finish button. And what that will do is actually run a script that generates our new project. And inside our new project, we get a number of files automatically generated based on the choices that we have actually made during the run through the project wizard. So in particular, we have an automatically generated startup file which sets up things like the exception vectors on the part. We have a main routine, which basically is a default main, so it contains a little bit of code that we'll see in a minute. We've got some initialization code related to LPCOpen being generated in the system init file, and then a couple of other additional files that are specific to the LPC11U68 and some of the functionality it provides. So if I just open up that main.c in particular, this contains the simplest possible LPCOpen project, which basically checks the clocks are set up correctly, calls an initialization function in the board support package to set up the board, and then calls a function that turns a LED on. So the simplest possible project you ever want to do is turn a LED on. So that's exactly what this actually does. And basically that means that you can then carry on and add the code specifically for your application based on the code that's been generated by the wizard. So just to make sure that actually has created something that works, I'm going to click on the build button and we've generated our final application. So we've shown you now how to build existing projects, how to create a new project. What we're going to do now is move on to actually debugging, but we're going to do that in a way that's going to more closely replicate the first time you actually run LPCXpresso. In other words, we're going to open a blank workspace with nothing inside it. How do we actually get going from that point? So what I'm going to do is select the switch workspace option inside the file menu, and this allows us to actually change the workspace that we're currently using. So it'll basically close down LPCXpresso and automatically restart it with the selected workspace. So the one I'm actually going to use is the one that's been highlighted there. So I'll restart it, and hopefully as long as I remember to clear it out this morning, we'll now have a blank workspace. Yep, there we go. So I cleared it and forgot to close the files there. So this more mimics how we're actually going to have the tool set up when we first get going. Now, we could just go off and use the new project wizards and create a new project, but we've not got that board support package library, we've not got the chip support package library. So the first thing that you will normally want to do is import probably some of the examples, but in particular the LPCOpen libraries. So we do that using the import projects option that we've got down here. And again, this runs another wizard. And we've got three options we can basically use here. We can import projects from an existing archive. So LPCXpresso projects are normally provided in zip format. We can import from a project directory. So basically you can select a directory, LPCXpresso will search that directory for existing projects and copy them into your new workspace. Or, and the place that you will normally start is by clicking the third option, which is the LPCOpen option down here at the bottom. And this will take us automatically to the LPCOpen website so that we can download the package for the part that we're actually using. And having downloaded it, we can then select it using the archive option. So I don't have an internet connection here now. I've already downloaded LPCOpen. So I'm just going to browse to it. And what I'm actually going to do is, this is a cut down version of the standard LPCOpen package for this particular board, to which I've added an extra example called basically breadboard twinkle, which is actually going to flash the LEDs I've got on my breadboard I've got connected here. So I'll select that zip file as the one that I want. You can see the archive has appeared there. I can click on the next button. And what we will then do is see a list of all of the projects that have been found within that zip. So normally when you start off by default, it's a good idea to select all of the projects that are found in the zip, particularly when you're looking at the examples, because you won't necessarily be aware of any independencies between projects. But the two that you really must import for using LPCOpen are the LPC board and the LPC chip projects. The rest you can select and deselect as you actually wish, but these two there are the key two ones which you always need to import. But in this case, I'm going to import everything. So I'll click on Finish, and our projects have been imported as described earlier. Okay, so we've now got some example projects. We're going to want to debug one of them. So how do we actually go about doing that? So the project I will actually debug is this breadboard twinkle project I mentioned a moment ago. So it's just a modified LED blinky basically, which flashes additional LEDs. So before I can debug it, I need to build it. Now in actual fact, when we launch a debug session using the quick start panel, that will automatically check whether we actually need to do a build, and if necessary will actually trigger one for us. But in the example case here, I'll manually click on the build button. This will go off. It will automatically build the breadboard twinkle project, but it will see the fact that the breadboard twinkle project is reliant upon the chip and the board libraries as well. So it's actually gone off and built those at the same time, and then built the application project at the end. So we've built our code. I'm now going to, as I said, click on the debug button. So if you watch the screen now, you'll see popped up there, we've got a little window saying initializing RedLink. And what that is doing is downloading the firmware that LPCXpresso uses in the debug probe on this board. So we've automatically downloaded the firmware. Having downloaded the firmware, the probe has re-enumerated on the USB bus and appeared as an LPC Link 2. And the tools have automatically gone off, interrogated the system to see what probes they can find. So in some cases you might actually have more than one probe. Most people won't, but it is possible. We then select which probe it is we actually want to talk to. So in this case, it's the LPC Link 2 we've got on our board here. So I'll click on OK. Get rid of the firewall warning. So it's just because I'm not connected to the network and was earlier. And the tools have now restarted. So what actually happens as part of that launch sequence is that our code has been downloaded into the flash, a breakpoint has been automatically set on main, and after the flash download is completed, the target has started executing, we have hit that default breakpoint on main. And so that's where we are at the moment. That's where the green line is that you can see there. You may also have noticed that as the debug session started, we had a new view appear up here, which is called the debug view. And this basically shows us the current stack frame. So this shows us again where we are in our execution of our application. So you can see that we're at the start of main in the file bbtwinkle.c. Now, if I just start executing our program, I can do that using the resume button here. So just to prove that it is now running, at this point now, we've now got some LEDs blinking, which I hope you can see. So having done that, I'll pause execution. So you can see that all of the run controls are up here in the icon bar at the top of the screen. So we've got the usual controls, so step, step into, step over, resume, terminate to actually kill our connection, so when we finished our debug session. And the other thing we can actually do up here is use a restart button, and this basically simulates reset, so we'll go back to the start of our program. So I'll just do that now. So as I said, we've got step, step over, so if we just step a couple of times, so if I hit to that point there, we've got a couple of other views down here which are interesting. So we've got the variables view, which will show us any local variables at the current time. We've got the expressions view, which is where we see any globals that we've expressed an interest in. So to view those, we just click on the spectacles and select them from a list. So let's just click on another one there, so you can see that being added. And you see at the moment, both of those have got the value 0. So if I just step over the system core clock update function, you'll see that one of the globals was actually updated as part of that call, and its new value has been highlighted in yellow, so we can see that it's changed whilst the code was actually executing. In a similar way, up at the top of the screen, you'll remember we've got the registers view. So the registers view shows us all of the registers within inside the CPU that's in the MCU. So again, if I do a step, so if we step into this board function, okay, so if I step again, so at the point, yes, there we go. So the registers have now changed. Again, the registers have changed. That's been highlighted for us in yellow there. The other thing that you'll notice is because we're now inside one of the subroutines, the stack frame information in the debug view has updated, so we can actually see that we're now in board init function. And if I change my variables and step again, you can see that the variables view here is updated as we've stepped into that next function. And it's actually quite easy to step up and down the stack frame. And as we do that, the variables view will update so that we actually see the locals that are in scope within each of those functions. So if I just step out of that function, or go up a level, and step out back to our main code. So what I'm going to do now is show you breakpoints. So the number of breakpoints that we can actually set depends upon which Cortex part we're actually talking to. So the LPC11U68 has a Cortex M0 Plus part which has got 4 breakpoints implemented in hardware. So at any one time we can have 4 breakpoints set in our code running from Flash. To set those breakpoints is quite simple. So here's my breakpoints view, which shows me what breakpoints are currently set. I haven't got any. So we can add one very simply by just double clicking in the editor view at the line that we want a breakpoint set. So you can see those breakpoints have appeared in the breakpoint view. I can delete them there. I can delete them by double clicking on them again in the window, in the editor view. Or if I want to, I can actually temporarily disable them so that they won't get hit this time through a loop, for example, just by unclicking them there. And you can see that when I did that, the icon that's displayed in the editor view was updated so that it's gone to a little greyed out version of its previous self. So if we re-enable it again, you can see it goes back to normal. So if I just run, you can see that, again, that breakpoint has been hit, our registers have updated, and so on. The final main debug view that I want to mention at the moment is the peripherals view. So this gives us the ability to view the register contents of the peripherals that we've got in the system. So the values of the GPIO functions, system control registers, and so on. So I've got a list of all the peripherals that are available to me in this window here. So if I just select the system control one to start with, you can see that we've had a new view pop to the front at the bottom, the so-called memory view, and this is displaying the values of those peripheral registers for us. So at the top level, we just get a numeric description typically, but if we open these out, in many cases, we'll actually get an enumerated version of that displayed. Just move the pointer. As you can see there, we've got enabled displayed. So those enumerations just make it easier for us to tell what the current state of the MCU actually is. Now, many of these registers will be read-write, some of them will be write-only, some of them will be read-only, and that's actually indicated in the views for you. But what I want to do now is just show you that I can affect the target MCU by displaying the GPIO ports. So if I remember correctly, let's just check the code, that top LED, so the one that's on at the moment, is pin 18 on GPIO port 1. So I'm going to actually open up that register inside the register view. So there's one, and we want port 18. So hopefully if I set that to 1, it's off. Excellent. Now if I set it to 0, it goes back on again. So we can actually update the state of the MCU from within the debugger. That's all basic standard debugging. One of the other nice bits of functionality that the Cortex M0 Plus parts have is built-in support for trace. So we can carry out instruction trace by using a small amount of the system RAM as a trace buffer. So we can access that inside LPCXpresso using the instruction trace view. And the simplest way of doing instruction trace is basically to turn on continuous recording. So it'll basically store in a ring buffer all of the instructions that are getting executed. So I'll just turn that on and then begin execution of my code again. And this time remove my breakpoint. So we've just got that running. You see the LEDs going up and down a few times. So if I pause execution and then go back down to the instruction trace view, I can click on the download trace buffer icon. And that downloads my trace, which gives me information on what program counter values, the disassembly of the instructions, and matches it back to the source code as well. Now, it's sometimes you can end up with the information you want not in your trace buffer because you're tracing instructions that have been executed lots and lots of times. So in this particular example, the LED blinky is very, very simple. It just has a delay loop in it, and we spend most of our time sat in that delay loop. So you can see that here from the systic delay. That's almost every instruction in our buffer. Now, one of the things that we've implemented inside the LPC11U68 is a couple of registers that allow us to turn trace collection on and off. So basically what I've got here in my code is a write to a register that turns trace collection off at the start of my delay loop and on again at the end of my delay loop. And I'm saying I don't want to collect that trace. So I can enable that by basically going into the advanced configuration options of the trace, and I have an option to enable trace collection and disable trace collection. So I'll turn both of those on, tick the tick box to apply it, and then basically begin execution again. So hopefully we're running again, so our LEDs are going up and down nicely. So if I pause execution and go back to my trace view and download it, we've now got a new set of instructions being collected. So at the top here, we can see we've got calls to the breadboard LED set routine. We're back in main. But if we scroll down a bit, we get this discontinuity in the trace collection, and that's basically where we've entered the sys-tick delay routine. We've turned trace collection off. At the end of it, we've turned it back on, and hence we've gone back to here. A couple of other bits of trace functionality that are worth highlighting are the fact that we can actually link our trace data into our source code. So if I select a function, you can see that the editor view automatically jumps to the instruction that matches the instruction I've selected inside the trace view. So if I again move down a bit further, and let's say that function there, we've again jumped to it. You may also note that we've got quite a lot of green statements being highlighted here. That's actually saying that we have executed those source statements as part of the trace buffer that has been collected. So that profiling information can just be turned on and off using an option inside the trace view. The other thing that we actually get regarding profiling is the numbers that we've got on the screen here. So that actually tells us how many times each of those instructions themselves exist inside the trace buffer. And again, that disassembly view will update as I select different instructions, as you can see on the right-hand side of the screen. So again, this just enables you to tie your trace collection up to your source code and an actual physical disassembly of your source code and link it to your trace buffer. We can use LPCXpresso board to debug another board, which in your particular system would normally be your own development board. And all that we actually need to do in order to support that is change the jumper settings that are on here to configure that we're going to use this to debug an external target. So what I'm going to do is unplug this one, plug this one in, and connect a debugger cable. So now when I turn that on, this board is actually now being powered over the debug connector there, which is why it's running. But what I'll actually do is, just to show that in action, we'll actually debug one of the other projects I've got on here. So I'll randomly pick the peripheral timer and debug that one. So again, we're downloading the firmware into the debug probe, this time on this board. It's downloaded the firmware. I click on OK, connects to the target, and then hopefully, if I click run, we've now got the LED blinking differently to how it was blinking previously. So we've just proved that we can use an LPCXpresso version 2 board to debug your own hardware. Okay. So that, I'm afraid, brings us to the end of this quick tour of using LPCXpresso. Thank you very much for attending.